Welcome to the next tutorial in three-phase induction motors. In this tutorial, we are going to solve few problems on equivalent circuit, and this will be the last tutorial for three-phase induction motor. So the first problem on the equivalent circuit is, if you have a 220 volt three-phase 4-pole 50 Hz star connected induction motor which is rated at 3.73 kilowatt. So this is the rating corresponding to three-phase, and the voltage that is being given is basically the line voltage. The parameters of the equivalent circuit are basically given. So here you have the one indicates the stator and two indicates the rotor. So R1 and X1 basically are the rotor resistance and the reactance that are there on the stator side, whereas R2 dash and X2 dash are basically the rotor resistance and reactance that are referred on the stator side, and B naught is basically the susceptance, that is the parallel branch. The core loss on the stator side is 50 watt and the rotational loss is 150 watt. For a slip of 0.04, determine the following quantities. So we have to determine the input power, power factor, air gap power, mechanical power, electromagnetic torque, output power, and the efficiency. So let us see the solution. So here we have the equivalent circuit of the induction motor. So R1 and X1 are basically the resistance of the stator, and here we have R2 by S, which is basically the load, mechanical load equivalent to the electrical load, and X2 is basically the rotor reactance. R0 and X0 are basically the shunt parameters. Here we can neglect the value of R0 and we can take only the value of X0, because R0 and G0 means the conductance and R0 means the resistance, is negligible. Hence we can consider only the value of susceptance. Then we can calculate the impedance in these two parts. That is, what is the impedance of ZAV. So in order to calculate the impedance of ZAV, we can follow the series parallel concept. So basically this part of the circuit is in series and which is in parallel with this part of the circuit, because we have neglected the R0. So we can put the values of parallel equivalent circuit R1 by R1 R2, R1 plus R2. So if you put this to find the equivalent impedance of the network, then putting the value of the susceptance, the resistance, load resistance referred to the stator side, the reactance referred to the stator side, and the resistances and the reactance on the stator side. So we will get the impedance as 9.29 angle of 22.5 degree. Now the net equivalent impedance Z01, which is seen from the stator side, is basically the sum of the equivalent impedance of Z1 plus ZAB. So ZAB we have already calculated, and Z1 is basically the sum of R1 plus X1. So we can get the value of the impedance, net impedance of the circuit as 10 angle 25.8. We have been given the three-phase voltage to 20 volt, but we need to solve it in single phase quantity. So first we have to obtain the voltage in per phase quantity. So we have to divide it with √3, and taking the 0 degree as the reference, we get the voltage as 127 angle 0. So the current which is flowing is basically, we know that current is equal to voltage by the total impedance of the network, which we have already obtained as Z01. So the current is equal to the voltage of the phase divided by the net impedance that we have calculated of the circuit. So we get a current of 12.7 angle minus 25.8. It means that the power factor of the network is basically cosine of the phase angle between the voltage and the current, which is 25.8. So this gives 0.9. So the air gap power which is there, so you have the stator and the rotor. So this is your stator and this is the rotor. So here you will be having the air gap power P2, which is equal to 3 times the current I2 square into R2 by S. This can be tell to be equivalent to 3 times I1 square into the total resistance of the circuit RAB. So 3 times the current. So current we have the magnitude 12.7 amps. So if here you have 12.7 square into the net resistance which is referred on the AB side, that is 8.58. So we have the air gap power as 4152 watt. Now the mechanical power developed PM, we know that the formula is 1 minus slip into P2, that is the rotor air gap power, which is 4152, the value of P2, and 1 minus slip will give you 0.96. So it gives 3986 watt as the gross mechanical power. Now we know given condition is that the synchronous speed is 1500 rpm. So the rotor is running at a speed nr is equal to ns1 minus s. So this gives you 1440 rpm. So the gross mechanical torque that is developed in the rotor is basically PM, that is the power of the mechanical power divided by 2 pi n by 60, where n is the actual speed of the rotor. This can be written as 9.55 PM by n. So we can substitute the value of PM that we have got, that is the mechanical power, and the actual speed of the rotor that we have got. So 1440 and 3986 we have to substitute in the equation of the gross torque, which gives you 26.4 Newton meter. So 26.4 Newton meter is the gross torque of the machine. Then the output power basically we can obtain by the value of subtracting the losses from the 3986 whatever we have got in the previous. So it gives you 3836 watt. Stator copper loss is being given as 50 watt. So the stator copper loss formula we can substitute as 3 times the current I1 square into R1. So current I1 is basically 12.7 square into the resistance which is 0.45. So we have 218 watt. So we have the core loss as 50 watt and the copper loss as 218 watt. Now this is the stator copper loss. So we have the current I1, whereas if we take the rotor, then we have to take the rotor current which is referred to the stator side, which is again 3 times I2 square into R2 dash. So it can be written as slip times the gross mechanical power developed P2 or air gap power P2. So here the slip is 0.04 and the air gap power is 4152. So it gives 166 watt as the rotor copper loss. Rotational loss is being given as 150 watt. So the total losses whatever we have is basically what is the stator core loss plus the stator copper loss plus the rotor copper loss and the rotational losses. So if we add all these losses and take the summation, so this gives to be 584 watt as the total loss in the induction motor. This means the efficiency is basically what is the output power, that is 3836. So this is your output power divided by output power plus the total losses. So losses we have 584, so we can substitute 584 and the output power is 3836. This gives you an efficiency of 86.8% for the induction motor. Second problem, we have a 115 volt 60 hertz 3-phase star connected 6-pole induction motor. So again 115 volt will be the line voltage of the 3-phase induction motor. Here we have a 6-pole induction motor and it is represented in the T circuit consisting of the stator impedance given. So this 0.07 plus J0.3 is the stator part impedance and an equivalent rotor impedance at the standstill condition. So we have been given at the standstill condition when the rotor is not rotating. This is the equivalent impedance of the rotor. And the magnetizing part G0 and B0 is also given. we have to find the secondary current, primary power factor, gross power output, gross torque input, and gross efficiency by assuming approximate equivalent circuit, assuming a slip of 2%. So we have to assume that the slip is 2%. So if we draw the circuit for the induction motor, which is referred on the rotor side, stator side, so we have the total resistance R01 is equal to R1, that is the stator resistance, plus R2 dash, that is the rotor resistance referred to the stator side, and X01 is similarly we can write X1 plus X2 dash. Here you have the RL dash, which is the electrical equivalent of the mechanical load, and this circuit is the approximate circuit because the shunt parameters are referred on the left of the circuit. So where you have the conductance and the susceptance. So what is the value of RL dash? RL dash means the load resistance referred to the stator side, and it is the electrical equivalent load, which is given by the formula R2 dash 1 by slip minus 1. We have the slip as 0.02 and the rotor resistance is 0.88. So this gives you 3.92 ohm per phase. Then the impedance, what we can obtain at these two particular points, ZCD. So we obtain that the impedance of the network, then the impedance of the network at the point ZCD, that is the terminal C and D, we can obtain as ZCD, seeing into the circuit. So these three parts of the resistances and the reactances are in series, and which is parallel with the shunt part. So we can obtain the impedance ZCD using the series parallel concept, which gives you 4.11 angle 8.4 degree ohms per phase. Then the voltage per phase is basically 115 by root 3, because 115 is basically the line voltage of the network, and we can see that I2 dash is equal to I2 here. So we can find the value of I2 as the total voltage divided by the total impedance, because the current is equal to voltage by impedance. So voltage is 66.5 and the impedance is 4.11 angle 8.4. So this gives you the value 16.17 angle minus 8.4 J. So here we will be getting the current I0, that is the no load component of the current in the shunt branch, is basically the voltage multiplied with the conductance minus J times the susceptance. So if you substitute the value of the voltage, which is 66.5, and the value of G0 minus JV0, we get the value of the current I0. So the PG value, that is the air gap power, is 3 times I2 square into RL dash. Current I2 we have already calculated as 16.17 as the magnitude, and load resistance referred to the stator side or the electrical equivalent of the load is 3.92, which gives 3075 watt as the power. Now the synchronous speed of the machine, we know that synchronous speed is basically 120 F by P, frequency is 60 Hz and pole is 6, so we have a 1200 RPM, the synchronous speed. So the actual speed NR is basically NS into 1 minus S, which gives you 1176 because the slip is 0.02. So the gross mechanical torque developed is basically 9.55 into PM by N. N we have already calculated as 1176 RPM, and the power PM we have calculated as 3075. So this gives 24.97 Newton meter as the gross torque. Now the input power P1 can be written as root 3 times V1 I1 cos phi, whereas the voltage V1 is basically the line voltage, which is 115. The current I1 is 21.7 because it is a star connected system. So for a star connected system, you will be having the line current is equal to the phase current. So here you have 221.7, and the cos phi value we know it is 0.804. So we'll give 3450 watt as the P1 value. So the gross efficiency of the machine is basically what is the output by input. So here you have the P1 is the input power. So this is our input power, and 3075 is our output power. So output by input multiplied with 100, we get an efficiency of 89.5%. That is the gross efficiency of the induction motor. Last problem for this tutorial, problem third, is basically the equivalent circuit of a 400-volt three-phase induction motor. So again, this is the line voltage because it is a three-phase induction motor, is a star connected winding, and the impedance for the stator, rotor and magnetizing branch is given. So it is referred to the stator at standstill condition when the rotor is not rotating. So find the maximum torque, slip at maximum torque, and power factor at a slip of 5%. So slip considered is 5%, and you have to use the approximate equivalent circuit of the induction motor. So these are the three parameters that we have to determine. So let us see the solution. So this is basically the equivalent circuit of the induction motor, which is the approximate equivalent circuit. So the approximate equivalent circuit, this is the shunt branch G0 and V0, and these are basically the series parameters with a load impedance, electrical equivalent of the mechanical load. So if we substitute the values of the parameters here, and then the air gap power P2 and the gross mechanical power developed by the rotor would be maximum when. So the condition is that when there is a maximum transfer of power to the resistance R2S. So the power will be maximum when you transfer the maximum power to the load. So this is our load. It will happen when R2 by S is equal to the impedance looking back into the supply source. So the condition for the maximum power to be delivered to the load is when the impedance looking to the system is equal to the load impedance. So if we do that and putting into the condition, R2 by the slip is equal to the total impedance of the network looking into the system, we can find what is the corresponding slip. So at what value of the slip the maximum power can be attained. So we can obtain the slip as R2 dash from this equation. We can use this equation to find the slip, R2 dash divided by the total impedance. So R2 dash is 0.6 and the total impedance we have put. So this gives you 0.29, which is 29% of the slip. So if we put to find the maximum value of the gross torque developed by the motor, we know the formula for the gross torque is basically what is the maximum power by the speed 2 pi ns by 60, and the power we can substitute as 3 times I2 square into R2S by slip. So here the unknown quantity is basically the current. So current we have to first determine. So current we can determine as the voltage divided by the total equivalent impedance. So total equivalent impedance and the voltage is basically per phase. So 400 by root 3 is the phase voltage, and this is the total impedance of the network. So current is basically 103.3. So now these current 103.3 can be substituted here, and the rotor resistance and the slip we can substitute, which is 0.29. So we get the gross torque as 351 Newton meter, assuming that the synchronous speed of the machine is 1500 rpm. Now using the equivalent circuit of figure B and a slip of 0.05, we can find what is the value of I2 dash. So I2 dash we can calculate as the value of the voltage divided by the impedance, and this voltage is basically per phase voltage. So we get a value of the current. Next, what is the no load component of the current? So no load component of the current I0 is basically the total voltage divided by the total impedance of the no load part. So we get the no load current. Next, the total current I1, that is the current drawn from the source, is basically the no load current plus the current that is taken by the load I2 dash. So we get 13.28 angle minus 24.4. So the problem being asked is what is the power factor of the system of the induction motor. So here we can see that 24.4 is the angle of the current with respect to the voltage. So cosine of 24.4 will give you 0.91 lagging. So this is the power factor for the system that we have been solved. So in this particular tutorial, we have solved few problems on the use of the equivalent circuit to find the different quantities like the power, losses, efficiency, torque, etc. So thank you for now.